여러분 안녕하세요. 딜레이가 돼서 미안합니다. 혹시 제 얘기가 말소리가 잘 들리는지 확인을 좀 해주실 수 있으실까요? 별 문제가 없으면 채팅창에 문제가 없다고 얘기를 해주시면 그러면 바로 진도를 나아가도록 하겠습니다. 네. 알려주셔서 고맙습니다. 그러면 진행을 하도록 하겠습니다. 왜 이러지? Alright, so last time we discussed the reactions of carbon compounds, which includes the addition of primary amine derivatives. So let us have a quick Korean review, and then we are going to move on further later. 네, 여기 한국말 리뷰를 잠깐 하도록 하겠습니다. 아민의 반응들, 아민이 아니라 카르보닉 컴파운드의 반응을 쭉 진행을 해오고 일반론까지 얘기를 한 다음에 특별한 경우가 이런 게 있을 수 있다라는 얘기를 했었는데요. 여기서 중요한 건 아민의 종류가 이런 것들이 있다라는 것을 알아두는 것. 일반식은 이렇게 되겠지만 종류가 이런 것들이 아민들이 있다라는 거, 그리고 다른 아민도 아니고 프라이머리 아민이어야 한다라는 거. 그 결과물이 아까 봤던 그 앞에서 봤던 것 같은 이런 결과물이 나오는 게 아니라, 여기서 나온 이런 결과물이 나오는 게 아니라 C와 N과의 이중 결합이 있는 그런 결과물이 나오더라라는 게 여기서의 포인트였습니다. 그 반응 자체가 이런 메커니즘으로 이루어지기 때문이다라는 얘기를 했었고요. 여기서 중요한 건 그 베이스가 이중 결합 부분에 있는 카본을 어택을 한다라는 사실까지는 똑같은데, 그 다음에 중간체가 이렇게 생긴 이후에 일반적으로 봤던 것과 그런 아까 봤던 그런 상황이 아니라 여기서 오히려 H가 떨어져 나가고 OH가 떨어져 나가는 그런 상황이 된다라고 얘기를 했었습니다. 그래서 특이한 경우로서 우리가 이걸 생각할 수가 있고, 앞으로도 계속 얘를 특이한 경우로서 이렇게 생각을 해주고, 그 이유까지는 우리가 아직은 너무 복잡하니까 몰라도 되고 일단 결과만 알자라는 게 지난 시간에 입장이었습니다. 그래서 나온 게 C 더블 본드 N이 생긴다라는 것이었고, 네, 물과 이게 같이 붙어 떨어지니까 물이 나오고, 그 다음에 이게 또 추가적으로 떨어져 나와서 결과적으로 물과 수소 이온 혹은 프로톤이 생성이 된다라는 부가물로서 사이드 프로덕트로서 이런 게 생긴다라는 얘기를 했었고요. 주 생성물로 이게 생긴다라는 얘기를 하면서 여기서는 이제 생성물이 이렇게 생기는 건 생기는 거고, 뉴클리오 파일이 프라이머리 아민이라는 사실 때문에 생기는 특성인데, 이게 pH가 상당히 민감하게 작용할 수 있다는 얘기를 했었습니다. pH가 너무 낮으면, too acidic하면, 그러면 카르보닉 컴파운드에만 프로토네이션이 돼야 할 텐데 됐으면 좋았을 텐데, 근데 당연히 이 프라이머리 아민도 이 비공유 전자쌍이 여기 있으니까 이 비공유 전자쌍 때문에 결과적으로 얘도 프로토네이션이 되겠죠. 그렇게 되면은 암모늄 염이 되면서 얘는 비공유 전자쌍이 이제 이용할 수 있는 비공유 전자쌍이 없으니까 더 이상 친액체로서의 뉴클리오 파일로서의 역할을 못하게 되겠죠. 그래서 에스딕하면 안 된다. 너무 에스딕하면 안 된다. 그리고 너무 베이직하게 되면은 이제는 정말로 원래 우리가 기대했었던 이 카르보닉 컴파운드, 카르보닉 스트럭처의 옥시전의 프로토네이션이 안 되니까 이것도 역시 문제다라는 얘기를 했었습니다. 그래서 중간 정도의 pH를 가졌을 때 가장 우리가 이상적인 결과를 기대할 수 있겠다라고 얘기를 했었죠. 그 이외의 카르보닉 컴파운드의 리액션으로서 우리가 또 다뤘던 게 옥시데이션입니다. 옥시데이션은 그 결과물들은 잘 알고 있는데, 여기서는 조금 특별한 경우들, 그리고 그냥 단순히 옥시데이션 해가지고 뭐가 생긴다가 아니라 그렇게 생긴 것들이 어떤 특성을 가져서 우리가 평소에 어떨 때 쓴다, 이런 얘기를 했었습니다. 여기 보시면 톨런스 레이전트라는 시약이 나오죠. 이거는 근본적으로는 그냥 은이온 용액인데, 그냥 은이온만 넣으면 불안정하니까 이렇게 옆에다가 리간드를 암모니아 리간드를 달아가지고 조금 더 안정적으로 보관할 수 있게 해주는 그런 시약이라고 보시면 되겠고, 여기 알데하이드를 넣으면 알데하이드가 지가 산화가 되면서 남을 환원시키는 역할을 하기 때문에 이건 산화환원의 근본 원리죠. 한쪽이 산화가 일어나면 한쪽이 환원이 일어난다. 항상 반드시 동시에 산화환원은 같이 일어나야 된다. 전자를 주고받으니까 당연히 주는 쪽이 있으면 받는 쪽이 있어야 될 거잖아요. 네, 그래서 이런 카르보실레이스로 산화가 되면서 이 실버 이온은 일가 이온은 메탈릭 실버 영가로 환원이 된다라는 얘기를 했었고요. 그래서 은거울 반응이라는 미러가 생기는 그런 반응이라고 해서 미러처럼 보이는 게 생긴다고 해서, 이 미러죠. 사실은 은이 유리 뒷면에 은이 코팅된 게 미러니까요. 그 거울이니까요. 그래서 이걸 은거울 반응인가라고 아마 우리말로는 그렇게 얘기를 할 거예요. 그리고 이걸 봄으로써 이게 결과적으로 제일 중요한 건 우리가 눈에 안 보이는 분자나 이온들을 가지고 반응을 시켜서 뭔가 인간의 눈에 보이는 어떤 결과물이 나왔다는 게 여기서 중요한 거라고 보시면 되겠어요. 그 아래 그 예시도 마찬가지지만, 그래서 결과적으로 알데하이드가 있는지, 특히나 제가 얘기를 드렸던 게 그 단당체 모노사카라이드라고 하는 단어였죠. 단당체가 일반적으로 알데하이드인데 수거 같은 거라고 했는데, 사실 수거는 저 2당이고 당이 두 개가 붙은 거고 나중에 우리가 할 텐데, 네, 단당체류가 알데하이드라서 이런 반응을 잘 보인다. 그래서 여기 단당체가 있나, 예를 들면 뭐 포도당 같은 게 있나 같은 걸 확인할 때 저 톨렌스 레이전트 집어넣어 가지고 은거울 반응이 딱 나타나서 거울 보인다 하면 이거 여기 단당체가 있구나 라는 걸 알아보는 그런 목적으로 쓰이는 시약이라고 보시면 되겠어요. 또 하나의 예시로서 키톤의 산화가 나왔습니다. 키톤의 산화는 보시다시피 원래는 일어나지 않을 일인데, 키톤이 데드 엔드인데, 근데 키톤을 특별한 종류의 키톤, 그러니까 여기가 수소였으면 알데하이드였는데 알데하이드보다 조금 더 키톤 쪽으로 한 발짝한 제일 작은 알킬 그룹, 메틸 그룹이 붙은 그런 종류의 키톤일 경우에는, 네, 예외적으로 얘가 카르복실레이시드로 산화가 된다라고 얘기를 했었습니다. 이때 이 산화를 시키기 위해서 써야 하는 시약들이 뭐 이런저런 게 있다라는 얘기를 했었는데요. 여기 X2 같은 게 X, 그러니까 할라이드가 쓰인다 그런 얘기를 했었는데, 결과적으로 이 CHX3에 해당하는 결과물이 사이드 프로덕트로 생긴다. 이게 그래서 요오드를 만약에 쓰게 되면, 아이오다인을 쓰게 되면 그러면 우리 말로 요오드화 포름이라고 부르는, 발음이 하기가 이상하네. 아무튼 그 CHI3라는 게 생긴다라는 얘기를 했었습니다. 이게 X가 I일 때 생긴다라는 거죠. 요오드화 포름 아이오드 폼이라고, 여기 어디 나왔네? 여기 있다. 아이오드 폼이라고 하는 게 나온다는 거고, 이것도 인간의 눈에 그냥 센 노란 게 보이는, 그런 색깔이 보이는 그런 결과물이 사이드 프로덕트긴 하지만 나오기 때문에 이걸 보고 원래 그 앞에 언노운을 우리가 산화를 시킨 거라면 언노운 안에 메틸 키톤이 있었구나 라는 것을 알 수 있는, 그러한 어떤 그 확인할 수 있는 지시약 같은 것처럼 우리가 쓸 수가 있다라는 것도 알아두시면 좋겠습니다. 캐니저로 리액션 앞에 리덕션. 네, 이건 뭐 알데하이드를 환원시키면, 아까는 산화였는데 좀 전에는 환원시키면 알코올이 나온다. 이게 프라이머리 알코올일 수도 있고, 키톤 알데하이드의 경우에는, 그리고 키톤의 경우에는 세컨더리 알코올이 나온다라는 얘기, 뭐 앞에서 알코올 때 했었으니까 그 역반응이라고 생각하면 쉽겠죠. 그리고 재밌는 반응이 캐니저로 리액션이었습니다. 캐니저로 리액션은 알데하이드라는 물질이 산화도 가능하고 환원도 가능하잖아요. 그러면 얘네 둘이 딱 만나서, 아까 산화 환원은 항상 같이 억한펜이 해야 된다고 했으니까, 그러면 하나는 산화되고 하나는 환원되는 것도 똑같은 시작점은 똑같은 알데하이드인데 가능하겠네 라는 생각을 할 수가 있겠죠. 그걸 그래서 이 양반이 옛날에 1600년대인가 1600XX쯤, 네, 그때 옛날에 이 양반이 이걸 의도했는지 발견했는지 저도 잘 모르겠어요. 근데 이 양반이 하여튼 이걸 보고를 해서 그 양반 이름을 따서 붙였는데요. 이탈리아 사람이고요. 알데하이드 두 개를 갖다가 염기성 조건에서 반응을 시키면, 하나는 프라이머리 알코올이 나오고 알코올로 환원이 되고, 또 하나는 카르복실 애시드로 산화가 된다라는 게 지난번에 그 얘기였습니다. 이거 뭐 이론적으로 당연히 가능할 거다라는 걸 알 수가 있는데, 아니 도대체 어떻게 어떤 딱히 다른 산화제나 환원제를 넣지 않고 그냥 자기 혼자만 뒀더니, 이런 알데하이드라는 하나의 스피시스만 뒀더니 얘가 지가 알아서 그렇게 산화환원이 동시에 페어로 일어나냐라는 게 궁금할 수 있는 점인데요. 네, 이런 메커니즘 따라서 일어난다라고 우리가 어, 공부를 했었습니다. 여기서 중요한 건 아까 얘기했던 염기성 조건이어야 한다라는 거예요. 그 제가 지난 시간에 얘기했지만 염기성이든 산성이든이라는 얘기가 나오게 되면은 반드시 산성이면은 이거 H 플러스가 엄청 많은 그런 상황이라고 생각을 해야 되고, 염기성이라고 생각하면 꼭 그런 건 아니지만 OH 마이너스가 엄청 많이 있구나라고 그렇게 생각을 하시면 쉽게 풀릴 때가 많습니다. 그래서 이것도 염기성 조건이다라는 것을 알아두시고 그럼 OH가 엄청 많은 상태네 라고 생각을 하고, OH가 과연 여기에 무슨 작용을 할까 우리 주 반응물에라고 생각을 시작을 하시면 쉽게 이해가 됩니다. OH- 잘 알려진 뉴클레오 파일이죠. 기억나시죠? 뉴클레오 파일 두 개로 이렇게 컬럼을 나눠가지고 한쪽은 스트롱 뉴클레오 파일, 한쪽은 위크 뉴클레오 파일이라고 해서 뉴클레오 파일 종류를 우리가 한번 공부를 했잖아요. 그 공부했던 내용들에 저 OH-가 뉴클레오 파일로서 등장을 했었습니다. 이거 기억을 꼭 하셔야 되고요. 그래서 뉴클레오 파일이 얘가 당연히 포지티브 차지를 따라 찾아서 헤맬 텐데, 마침 이 알데하이드, 벤자알데히드에 보시면 카르보닐 스트럭처가 있고, 카르보닐 스트럭처 하면은 반드시 카르보니 positively partially positively charge를 띠고 있구나라는 것을 그냥 바로바로 떠올리셔야 돼요. 사실 저 C 더블 본드 O의 모든 이 중요한 반응의 그 근원은 얘들의 polarity에서 나옵니다. 차지가 있다 없다, 어디에 있냐, 어떤 차지가 있냐가 중요한 거고, 자 OH-도 그래서 이 카본을 어택을 하죠. 이건 정전기적 인력이기 때문에 여러 번 강조했지만 정전기적인 인력이기 때문에 너무 간단한 자연스러운 그런 현상이라고 보시면 되겠어요. 그렇게 해서 그렇게 해서 진행이 된 이 어택이 결과적으로 이런 중간체를 낳게 됩니다. 이 중간체 테트라이드럴 구조를 가진 애가 원래 여기서 이 부분만 따지면 뭐라고 했죠? 이 부분 구조? 네, 플라나하죠. 근데 여기서 중간체가 되면은 얘가 이제 이중결합이 풀리면서 sp3 하이브레이션을 하는 상태가 되기 때문에 사방팔방으로 가지가 뻗어서 4개가, 그래서 테트라이드럴 스트럭처 쪽으로 가게 됩니다. 이게 이 중심 카본을 중심으로 해서요. 그리고 여기서 OH가 붙고 나면은 결합이 생기는데, 이 카본이 그럼 나 여기 못 견디겠어 하고선 이중결합 하나 풀어버리죠. 결합을 5개 가질 수 없잖아요. 그러니까 하나를 풀어서 결합을 4개로 유지를 하고, 이중결합을 풀면서 그 이중결합에 있던 2개의 전자를 어떻게 해요? 이거 지가 어떻게 할 수 있는 방법이 없잖아요. 카본 스스로가 다룰 수가 없겠죠. 그래서 너 마침 전자 좋아하는 특성을 가지고 있기도 하고, 너 마침 빈자리도 있으니까 네가 이것 좀 맡아라 하고서는 억시전 쪽으로 떠밀어요. 그래서 이렇게 억시전이 지 거가 아닌 전자, 카본의 전자 하나까지도 자기가 갖게 되기 때문에, 떠맡게 되기 때문에 음전하를 띈 상태가 되는 걸로 표시가 된 거예요. 자, 근데 이렇게 되면 일단 떠맡았는데 억시전 입장에서는 어떻게 돼요? 이거 뭐야, 왜 이렇게 내가 점전하를 포인트 차지를 가지고 있어야 돼? 라는 생각을 하게 생각을 진짜 하지 않겠죠. 근데 생각을 하게 되겠죠. 점전하는 뭐다? 네, 가장 불안정한 요소이다. 우리가 다루는 이 세계관에서, 유기재료화학이라는 이 세계관에서 점전하는 굉장히 그 안정성을 해치는 불안 요인이다라고 우리가 반복적으로 학습을 했었습니다. 그게 지금 딱 여기 억시전에 나타난 거예요. 그러니까 억시전 어떻게 해야 돼요? 이 불안 요인을 해소를 해야겠죠. 해소하기 위해서 어떻게 할까? 싫어, 왜 이걸 나한테 떠맡기고 난리야 하고 다시 탄소한테 그걸 전자를 다시 떠넘겨요. 우리 같이 쉐어하기로 했잖아. 유지여서 왜 나보고 다 맡으래? 라는 그런 얘기를 하는 거죠. 그게 바로 여기 나와 있는 이 화살표입니다. 전자를 다시 주는 거예요. 자, 그렇게 되면 이제 카본 입장에서는 어때요? 그 5개의 결합을 내가 유지할 수 없기 때문에 4개만 하려고 하나의 결합에 해당하는 2개의 전자를 산소 쪽으로 일단 떠밀었는데, 산소가 다시 이거를 갖다가 나한테 맡기네. 어쩌지? 나 이거 감당할 수 없는데. 네, 그건 탄소는 4개까지만 가능하니까 감당할 수 없겠죠. 그래서 탄소가 한 게 뭐냐? 그러면 딴 결합에 딴 전자 2개를 덜어내서 다시 결합을 4개로 유지해야겠네 라는 생각을 하게 돼요. 그때 어제 제가 얘기를 했었죠. 그러면 여기 녹색 수소와 그리고 파란색 OH 2개가 그다음 떨어질 수 있는 가능성이 있어요. 이 벤젠고리는 굉장히 안정적으로 탄탄하게 연결되기 때문에 얘는 감히 떨어질 생각 못하고 가볍고 작은 것들, 그래서 상대적으로 약하게 결합된 이런 수소나 OH를 떨어뜨릴 생각을 하게 돼요. 여기서 OH를 떨어뜨리면 어떻게 되나요? 그럼 제가 어제 이것도 얘기를 했었죠. 여기서 OH를 떨어뜨리면 다시 그냥 왼쪽으로 하는 거예요. 역반응. 처음 반응 상태로 하니까 이거는 네트 리액션이, 그러니까 이거 네트를 뭐라고 할까요? 순수하게 우리가 반응이 간 거가 제로죠. 간 게 없다는 거랑 똑같은 거잖아요. 그래서 고위치가 떨어진 경우는 우리가 생각할 필요가 없어요. 그냥 이게 평형을 이루면서 왔다 갔다 하고 있는 와중에 다시 뒤로 간 거가 잠깐 나왔구나라고 생각하고, 뭐 실질적으로 이루어진 반응이 없으니까 그건 이제 생각할 필요가 없이 무시하면 되는 거고요. 진짜로 이제 뭔가 네트 리절트가 있는 그런 경우가 저 OH, 녹색 OH가 떨어지면 이제는 뭔가 새로운 반응이 생기는 게 되는 거죠. 새로운 반응이 되는 거죠. 네, 그래서 이 네트 OH가 네트 반응을 우리가 실제로 0이 아닌 실제로 뭔가 결과가 있는 반응을 만들기 위해서 저 H를 떨구게 되면, 근데 H를 떨구는데 어떻게 떨궈야 돼요? 지금 우리 탄소가 반응을 하기 싫어가지고 이걸 떨구고 있는 거잖아요. 네, 근데 반응을 하기 싫어서 떨구고 있는 건데 저 반응을 우리가 어, 반응이 아니라 결합을 떨구기 위해서, 그럼 결합을 떨궈야 되니까 여기는 이 녹색 부분의 요 결합, 사실은 전자 두 개로 이루어진 이 결합을 같이 수소와 함께 떨궈야겠죠. 그래서 제가 어제도 강조를 했었죠. 수소와 함께 전자 두 개가 떨궈진 그 상황. 수소인데 전자 두 개가 있다. 이거 뭐예요? 네, 하이드라이드 아이온이라고 우리가 일컫는다라고 지난번에 우리 알코올에 가지고 엘리미네이션 얘기할 때 처음에 등장했던 그 물질인데 오늘 다시 등장을 했습니다. 하이드라이드 아이온이 떨어지게 돼요. 하이드라이드 아이온이 떨어지면 다시 또 얘는 얘 입장에서는 수소 이온, 수소 음이온 입장에서는 이게 뭐야, 내가 불쌍한 조그만한 원자인데 내가 전자 두 개씩이나 떠맡아야겠어. 나 원래 전자 없는 프로톤이라는 이름으로 잘 알려주고 프로톤인 상태가 가장 해피한데 뭐 두 개도 옥텔룰을 만족시킬 수 있는 거이기도 하지만 원S를 다 채웠으니까요. 그러니까 안 되는 건 아닌데 나도 어차피 이거 불행해. 어쨌든 차지가 있는 거니까 포인트 차지 싫어. 어떻게든지 이걸 해소해야겠어 라는 생각을 가지고 적절히 또 먹잇감을 찾아 헤매요. 얘도 H 플러스 H 마이너스니까 뉴클레어 파일일 거잖아요. OH 마이너스와 마찬가지로. 그래서 다른 요즘 무수히 있는 게 요 벤자일디드니까 다른 벤자일디드 옆에 반응 안 한 벤자일디드 있네, 너 일로 와 하고서는 요런 식으로 요렇게 카본을 다시 어택하게 됩니다. 뉴클레어 파일은 카본을 어택한다 라는 거, 계속 지금 똑같은 원리가 적용이 되고 있는 거예요. 다만 걔가 원래 1번 벤자일디드냐 아니면 2번 벤자일디드냐에 따라서 다르게 될 뿐이죠. 두 번째 벤자일디드에 이렇게 하이드라이드 이온이 어택을 하게 된다라는 얘기를 했었고, 그러면 다시 또 이 카본 괴롭죠. 나 지금 번드 4개 가지고 행복하게 살고 있었는데 갑자기 웬 H- 와서 번드를 들이대네. 내가 번드가 5개가 있는데 결합이 불행하고 힘들어 라고 해서 다시 또 어떻게 해요? 네, 다시 또 이중결합을 해체를 할 수밖에 없겠죠. 하나를 풀어서. 그래서 산소 쪽으로 전자 두 개를 들이밀 수밖에 없겠죠. 생각을 해보면 이걸 지금 이 이중결합에서 이게 풀어지는 거, 여기 이 현상, 이거 이 현상, 지금 공통적으로 카르보닐 그룹에서 일어나는 이 현상을 가지고 혹시라도 왜 저게 이중결합이 풀어져요 라고 생각할지 모르겠는데, 여러분 생각을 해보면 나머지는 다 시그마 번드인데 저 이중결합 부분에 저 풀어지는 번드만 파이 번드예요. 파이 번드는 시그마 번드보다 원래 근원적으로 약할 수밖에 없다라는 거 일반 화학 시간에 들어서 다 알고 있을 거라고 생각을 해요. 그래서 파이 번드가 떨어지게 되고 죄송합니다. 제가 목이 오늘 안 좋아서 약간 톤을 낮춰서 하겠습니다. 파이번드가 떨어지게 되고, 파이번드가 떨어져서 다시 전자가 이렇게 산소 쪽으로 가게 되면 또 음전을 띠게 되겠죠. 그래서 음전을 띠게 되면 이거 음전아 어떻게 하는 상황이 되는데, 자 일단 앞에 것부터 정리를 해보면, 자 앞에 얘 여기 그 원래 1번 탄소였다가 지금 인터미디트로 갔던 요 1번 탄소 1번 벤자일디드, 얘는 아까 녹색 수소를 떨어뜨렸다고 했잖아요. 그리고 다시 저 보라색 산소의 이중결합이 탄소와 함께 생기게 된다라는 얘기를 했었고요. 그럼 얘는 뭐예요? 결과적으로 여기 벤젠 링 이렇게 있고, 그리고 여기 카본 있고, 보라색 탄소가 다시 이중결합이 생겼고, 그 다음에 저 하늘색 OH가 그대로 유지하게 되는. 자, 그래서 얘는 뭐가 됐어요? 네, 드디어 카르복실시드가 됐어요. 근데 이렇게 된 후에 저 옆에 있는 이 탄소가 다시 산소가 이 탄소가 다시 음이온을 아까 가지게 된다, 음전을 가지게 된다라고 그렇게 얘기를 했었잖아요. 그 이중결이 풀어지면서. 그래서 얘를 해소를 해야 된다라고 했는데 마침 프로톤을 주기에 되게 좋은 종류의 물질이 옆에 있어요. 뭐가요? 여기 얘예요. 카르복실 애시드. 여기 COH 카르복실 애시드는 아직 우리 카르복실 애시드 오늘 이제 하게 되겠지만 안 했지만 이게 저 산이라는 거 다 알잖아요. 산이 뭐예요? H 플러스를 주는 물질을 산이라고 하잖아요. 그래서 이 OH의 COH 부분에 이 H 플러스를 얘한테 줘요. 그래서 얘따 네가 먹어라 하고서는 그래서 이 부분은 OH가 되겠죠. 원래는 O 마이너스였는데 H 플러스를 받아서 OH가 돼서 행복해진다라는 그런 상황이 되겠습니다. 그래서 결과적으로 이 OH가 된 요거가 바로 얘고, 그리고 카르복실릭 애시드에서 H 플러스 하나가 떨어져 나간 부분이 바로 얘가 된다라는 그런 얘기를 했었죠. 벤질 알코올 반족 애시드라는 얘기를 했었고, 그러고 보니까 디스프로포셔네이션 얘기를 지난번에 안 했던 것 같네요. 요거 저 다음 주 화요일에 이 부분만 달랑만 하는 걸로 하고 오늘은 리뷰를 그냥 한꺼번에 해버릴게요. 사실 리뷰가 안 했으니까 리뷰가 아닌데 뭐. 네, 그래서 그 인터미디트 부분에서의 하이드라이드 아이언이 트랜스퍼를 옆에 있는 다른 CW분으로 가게 된다라는 얘기를 했었고, 자, 중요한 건 여기서 용어예요. simultaneous 동시에 일어난다는 거에 뭐가 oxidation하고 그다음에 reduction이 동시에 일어난다라는 그런 상황인 거고, 네, 이런 동시에 일어나는 reduction과 oxidation을 가리켜서 disproportionation이라고 한다라는 이 용어를 여러분이 알아두시면 좋겠습니다. 이거는 제가 영어로 그때 그 카니제럴 리액션 하다가 저 부분을 얘기를 안 했던 것 같은데, 네, 따로 얘기를 해야겠. 잠깐만, 이거 얘기를 안 한 게 아니라 이게 하기 전에 끝났겠죠 아마. 일부러 하는 게 아니라. 네, 아무튼 근데 네, 오늘 한국말로 여기까지 하고 그리고 저 부분은 영어로 다시 이 부분을 새로 영어로 하겠습니다. 화요일에요. Alright, so that's the end of the Korean review, and then now we are moving on to what we have to discuss today. It's still about the same reaction or reactions, but we are going to check out how those reactions could be applied to prepare something useful. The first example as an application is what? Nanoparticle surface modification. So nanoparticles, let us consider why nanoparticle surface modification is necessary. Do we have it here? Okay. I'm pretty sure you all have the experience in testing your sample using the quick test kit. For example, for COVID-19, something like that. So you inject your sample, like your liquid from your nose or liquid from your throat or things like that, and then it develops, and then there are lines somewhere here, and then if you are lucky, you have only one line, and if you are unlucky, then you have one more line like this. These lines are actually nanoparticles. Nanoparticles are running through the fluid, and then at a certain point, if your sample has, your nose sample or your throat sample has the specific proteins or viruses, then particles are supposed to stick here and stick here. So eventually you are actually looking at the nanoparticle assembly on the test strip. So that's possible only because nanoparticles can recognize particles can recognize the virus or proteins, and to do so, particles should be modified with antibodies, because antibodies can recognize the viruses or antigens or proteins. So that's the brief background introduction, and so let's see the detailed reaction for the antibody functionalization or surface modification. So in the inventory, meaning that you have selection, you have the choice to buy or purchase any of those particles. These are particles are sold in the market. You can buy them if you have money. So particles can have different chemical functional groups like COOH or NH2 primary amine group or aldehyde group or thiol group. This SH is called thiol. So such various functional groups can be on the surface of nanoparticles from the beginning. Your job or your mission is what? To add antibodies on the surface of nanoparticles for applications like this. And antibodies have the primary amine groups by nature at the end. So maybe you can consider the reactions of the surface functional group of one of them with the primary amine group of the antibody. So the best reaction maybe could be what you just learned, the aldehyde with reaction of aldehyde with primary amine group to have this kind of bond. So they are bonded, they are conjugated, they are bonded. There are many possible expressions to describe this phenomena. But basically, these are added together, bonded together. And then actually, this is not the only antibody. There could be other antibodies bonded here, or an antibody here, antibody here. So there are so many antibodies around nanoparticles. So particles can, again, recognize the virus or proteins and then eventually stick to the designated location of the strip. And then if there are so many particles, then nanoparticles are not visible by itself usually because it's too small. But there are so many particles bonded to or assembled in this area or in this area of the strip, then eventually you will be able to recognize that, oh, there are, actually you cannot see the particles, but you can see the band, which is based on the assembly of the particles. So you can understand that, oh, I'm infected, I got COVID-19, or this could be used for other tests like the pregnancy test, which is very popular, which that's also based on the antibody and antigen reactions, and then those antibodies are on the nanoparticle surface so that you can recognize them easily. We may have a chance to talk about this kind of applications later more, but just for now, to understand that there could be the conjugation reaction for the antibody and nanoparticles using the reaction of aldehyde and primary amine. The next example is the polymerization. So probably you will learn this kind of reaction later in a subject or in a course related to polymer or polymer science. For now, however, we can quickly check what could be done using the reactions that we learned. The first reagent shown here, here, it's melamine. So here, amine, primary amine. So it looks like benzene ring, but actually it's a heterogeneous ring. It's not only composed of carbon atoms, but also nitrogen atoms. And moreover, there are 3 primary amine groups that are attached to the aromatic ring. It's called melamine, and if we react with this melamine with glutaraldehyde is a conventional name actually. It has glutar and aldehyde combined together. It has the 2 aldehyde functional groups at each end of the alkane chain. So if we combine them together, then again the same reaction will take place like this. Yeah, it has the N double bond C right here, and then N double bond C right here. And that's not all. It's just one single reaction, but actually it may have the combination right here and then right here. And also there are more primary amine groups and more possibly glutaraldehyde. Right here, and again with something else here, and so on. Eventually this will keep going and on and on. There are multiple sites at each molecule, multiple sites, 3 sites in the melamine structure and 2 sites in the glutaraldehyde structure. So there could be multiple bindings, multiple conjugation, and multiple and then even it will go on and on to become larger and larger. So finally, you may have something like this. It's just a scheme. Actually, there are more like this. This M means melamine. So there are more. So it's will be like larger. And then eventually you will be able to see the morphology of this polymer using electron microscope. You see the rough structure, texture of the polymer. So it's based on the continuous nucleophilic addition, as we learned, the primary amine to the aldehyde, and then in all directions. So eventually, as written here, 3-dimensional polymer networks, which is shown here. That's the resultant after the polymerization. So you will learn in such subjects related to polymers, there could be many possible ways or methods to react the monomers to polymerize them. There are many possible reactions, and this is just one single reaction as an example, but still it's worth because it has something to do with the reactions of carbonic compound, particularly aldehydes with primary amines. All right, so that's the end of week 8, and we're going to move on to week 9. Here we have a single topic, carboxylic acid. So previously, until last year, until last year, this chapter was actually a combination of carboxylic acids and amines together. And then I thought probably we may need to dig into more details. So I have a separate section for carboxylic acids for week 9, and then obviously week 10 will cover amines. So be prepared. All right, so let's see what we have here. Yeah, we only have 20 slides, so it will be easily over. Unique synergy. So if you take a look at the structure of carboxylic acid, it's combination of C double bond O and OH. So it's sometimes confusing whether it has the properties of carbonyl compounds and also properties of alcohol compounds. It's not always like that because that's why we call it synergy. It's something else. When they are combined together, now we have a unique, interesting properties, which are totally different from the original properties of the carbonic compounds and alcohol compounds. However, still there could be possibilities for the properties of carboxylic acids based on the basic fundamental structures of the carbonyl groups and hydroxyl groups or alkyl functional groups. Let's see. So this carbonyl group, still it's possible. It's not possible. It's true. It's true that this carbon atom of the carboxylic acid functional group, it's still a site for nucleophilic attack, isn't it? It should be, because it's bonded to very electronegative oxygen 1 and oxygen 2. So therefore, this carbon of the carboxylic acid group, functional group, should be partially positively charged. And also, hydroxyl group, it may have something to do with the loss of proton. So yeah, we all know that carboxylic acid functional group will release H plus. That's why we call it acid, right? And this property has something to do with the hydroxyl group, and we'll see the examples later about this OH only and maybe CO only one by one. But once they are combined together, then actually they are different. And then you will see what's different from the individual CO and the OH groups. We don't need to do this, but it's not only about nomenclature. It's more like nomenclature with conventional names. Right. So at the beginning of the semester, we stick to the IUPAC nomenclature, which is official, and then it's just the standard, and everybody understand that, and I think that's enough for now. But in fact, once you move on and then once you get a job in this related fields, or if you move on to graduate schools or whatever, in reality, in real life, as I think I discussed this before, conventional names are more used sometimes than IUPAC names. So you need to know the both IUPAC names and conventional names, and depending on which area you get a job in, or which area you work in, sometimes you need to use more conventional names than IUPAC names. It's a matter of language. As I told you, it's not about academia. It's not about study. It's not about education. It's a matter of human language, and then it's not easily changed. So the point is, give it up. You cannot change the convention. So follow with the convention and do what others do. To do so, you need to know the conventional names of materials as well, both the IUPAC names and conventional names together. That's my conclusion based on my observation. I don't think that's fair. As I told you, I am a supporter for IUPAC nomenclature. I think that's best. Like we use 표준어 in Korean. But still, there are people who like to use dialects, 사투리 or 방언. They feel they love them. They feel it's better, or sometimes they feel more friendly or whatever, and they are respected. So same is true with maybe this kind of issue in academia. So conventional names, maybe some people like to use conventional names than IUPAC nomenclature. So we need to follow them. So at least we need to know what kind of conventional names exist. So in this slide, we may want to talk about that. There are several carboxylic acids. Here we have one carbon and one carbon with H, one carbon with it's CH3. One carbon with methyl, or let's say 2 carbons, and then 4 carbons, and then 18 carbons. I think it's not necessary, so let's delete them. It's confusing, sorry. And then this acid, which is methanolic acid in terms of the IUPAC nomenclature, is called the formic acid. methanoic acid, ethanoic acid, and butanoic acid, and octadecanoic acid. When we have 18, it's octadecane. So octadecanoic acid. These are the IUPAC nomenclature in the parentheses, and then the conventional names are shown in bold. Formic acid, acetic acid, you know that, butyric acid, and stearic acid. They have their Korean names, and I think they are actually translation of the English names. So formic acid is also called ant acid, because um, it has it's included in ants, and then when there's an ant bite, then you feel pain because of this formic acid. Um, and also, this is the reason why methanol is harmful. When you take methanol, methanol itself is okay, but after the reactions in your body, methanol is oxidized into formic acid eventually, and this formic acid is extremely harmful in your body, so that you become blind or you become dead. That's what we discussed before. And formic acid is the name of this methanoic acid, conventional name. Acetic acid, I think you know what acetic acid is. It's the ingredient of vinegar. Butyric acid, it's butanoic acid. It has very bad smell, rancid butter smell. Yeah, that's the description for butyric acid. rancid, 상한, 시큼한, 썩어가는 아마. 네, in Korean. And stearic acid, that actually has a very long chain. So remember, when we discussed the duality of our course, like hydrophilic OH and hydrophobic tail. It's similar here. Stearic acid has very long hydrophobic alkyl chain tail, and hydrophilic head group. The difference is not just OH, but it has the COOH. Oh, I think that's misleading. It should be, the parentheses should be something like this. There are 16 carbon atoms, so not here. It's not here, but it's here. 16. 1, 2, 3, 4, 5. Actually, it should be 11. Yeah, whatever. Anyway, the total C18. All right, so that's the names of typical representative carboxylic acids. And also, there could be dicarboxylic acids. There are 2 COOH groups. And the examples are shown here. Succinic acid and malonic acid, depending on the number of carbon atoms between the COOH. And check out the structure of malonic acid as well. It will help. And benzoic acid, we have COOH that is bonded to the aromatic ring. We just saw as a result of the Cannizzaro reaction, right? After the oxidation of benzaldehyde, we have benzoic acid as shown here. So these are brief review of the carboxylic acid. Here, carboxylic acid, and then IUPAC nomenclature uses numbers. We already know it, but common names. For example, if there's a butyric acid right here, we also need to designate this carbon, and this carbon. So when we want to designate those or indicate these carbon atoms of the carbon chain, there should be a certain way. IUPAC nomenclature, as shown here, uses numbers, and I think that's much better. But common names use Greek letters like alpha, beta, gamma, and then it starts with the second carbon atom. So if you take a look at that, for example, in case of butyric acid, I don't know why, but well, that's what people has been done so far. People have been done so far. So this carbon is just carbon. There's no designation. This carbon is alpha, beta, and this is gamma. That's how the carbon atoms are designated. Again, that's not what I made. It's what people, old people made. So, well, we have to follow that. So yeah, here is the designation of the carbon atoms. And then also we have an introduction of a very bad material, which is called GHB in English. It's a drug, very bad drug. It was a very big issue a few years ago. So before we move on, let's take a look at the structure. It's a COOH. Yeah, okay. And then one carbon atoms. One, two. Oops, sorry. This is one, and this is two, and this is three, and this should be four. I'm sorry. Yeah. So that's how we name or number the carbon atoms following the IUPAC nomenclature. And as we discussed, if we follow the conventional nomenclature, this is alpha, beta, and gamma. And then at the fourth carbon or at the gamma carbon, there is an OH functional group as shown here. So it has OH, one more OH, in addition to the butyric acid. Its name is GHB. Why is that? Because its hydroxyl group is bonded to the gamma carbon. So we call it gamma hydroxy butyric acid. That's the conventional common name. And in Korea, it's known as mulbong. It's a very bad, serious drug. You shouldn't be in touch with or in contact with this kind of thing at all in your whole life. But some people do. And its IUPAC name is 4-hydroxy. I'm pretty sure you all know this. 4-hydroxybutanoic acid. The problem of this material is that it's colorless, odorless, and it's kind of liquid. It's not salt, it's liquid. So when you add it to water, it blends very well without any trace. So you cannot tell whether it's just pure water or water where GHB is dissolved or mixed. So it's sometimes used crimes, and yeah, it was a big scandal in 2019, in the club in Gangnam, Burning Sun. Are you old enough to remember this event? Well, anyway, so there was a Korean K-pop group, Big Bang, and there was a member called Seung Lee, and he was the director or manager or owner of the club, I think. And then he was involved. He was known to be involved in this event. There was a crime in this club using this drug, and it was a big issue, social issue at the time, because that scandal involved drug trafficking and even police corruption and exploitative crimes. Yeah. So I even do not want to recall this event, but still, we should be careful first, and second, we should know what material was used, and third, we should be able to call its name in both ways, in using the IUPAC nomenclature and using the conventional nomenclature. And then it's GHB, which is based on the conventional name shown here. Okay, so yeah, that's just an example. And then let's move on to the physical properties of carboxylic acids. So carboxylic acids are known to have a structure, dimer structure like this, based on their hydrogen bonding. So this is hydrogen bonding, and this is hydrogen bonding, and then when two carboxylic acids are positioned in this way, then obviously this is a suitable and the best way probably to form a dimer, and then it's very strong. it's not like one with other one and the other one and the other one using one single hydrogen bond, and so on and so forth. But it's just two hydrogen bonds between the two entities, two substances. So it's stronger than just one single hydrogen bond, and therefore it's hard to break. And naturally, they are supposed to form such a dimerized form, and it's a metaphor by saying lock. So because of that, actually those carboxylic acids play a role. I'm sorry, behave like materials having much higher molecular weights. Let's say the molecular weight of carboxylic acid is, let's say, 50 the, for a single molecule, and then its behavior is just like the materials having molecular weight of 100 because of this dimerized form. So yeah, the boiling point is always what we discussed with regarding the physical properties of materials. Carboxylic acids boil at higher temperature than similar alcohols. Here we have an example. Formic acid has molecular weight of 46, and then boiling point is approximately 20 degrees higher than that of ethanol. And the reason is because of this dimerized form. Practically, molecular weight has been increased because of this dimerization. And why do they dimerize? Because of two hydrogen bonds, and it doubles their molecular weight, and extra energy is required to break not only the van der Waals forces of the larger dimerized forms, and also the physically to disrupt the hydrogen bond between the individual carboxylic acid molecules. So we need 1 and 2, and that's why we need more energy, thermal energy, to boil carboxylic acids. So it's an interesting material. As always, let us also think about the solubility of carboxylic acids. And yeah, as always, so we will think about the role of the functional group, carboxylic acid, and also the role of the carbon chain. And if carbon chain is short, then they can be easily dissolved in water, or they are much miscible in water because of the polar COOH, and also because of the hydrogen bonding formation of the carboxylic acid functional group. They can form the hydrogen bond because of this hydrogen, right? Unlike the carbonyl compounds. However, carboxylic acid functional group is favorable for dissolution in water. Meanwhile, the alkyl chain is hydrophobic, so the longer alkyl chain is, the more hydrophobic is, and the less it is dissolved in water. So up to 5 carbon carboxylic acid, it's called valeric acid, 1, 2, 3, 4, 5. It's partly soluble in water. That's kind of the point where we can consider the dissolution of carboxylic acid in water. From 6 carbon carboxylic acids, such as caproic acid, 1, 2, 3, 4, 5, 6, okay, and then longer carbon chains, then they are practically insoluble in water, and that's because of the long hydrophobic alkyl chains. So, oh, by the way, one thing interesting with carboxylic acid. So, if you take a look at the dimer structure like this, you know that it's more like the central polarity, it's polar part, but outside, right here and here, it's non-polar because of the alkyl chains. So central polar part, and then outside the non-polar part, And this, because of the structure, this unique structure, um, it's less hydrophilic than the individual molecules. The supposedly less hydrophobic, I mean less hydrophilic, because the polar party is hidden, kind of hidden at the center. And then what the solvent sees is just the outside R and R hydrophobic area. So it's not as hydrophilic as expected from the molecular structure. Um, and 누가 somebody said something in the chatting room. 이게 뭐죠? 점인데. 포프라 168님 혹시 뭔가 점을 찍은 이유가 있나요? 네, 혹시 쓰다만 거면 써주세요. Anyway, so that's why it's less hydrophilic, or let's say it's less hydrophilic than expected, and therefore carboxylic acid can be soluble in less polar solvents such as chloroform or ether. I gave you an example of chloroform right here. Yeah, it's less polar, but still they can be dissolved in, the carboxylic acids can be dissolved in such less polar solvents because of the structure of the dimers like this. 쉬는 시간. break time. 아니요, 우리 45분 예정대로 쉬도록 할게요. We're going to have a break time from 2:45 for 5 minutes as we have done so far. From 2:45. The break time will begin at 2:45. All right, so after that we will do some math. I don't like math, but we're done, right? Yeah, I don't like math, but we have to check it out because it's an important property of carboxylic acids. Most of you already know that carboxylic acids release H plus or proton to become COO minus, an anion, and then H plus is released. And actually, there's no H plus, individual H plus. It's actually H3O plus, an oxonium ion, because H plus is taken by water molecules in the solution. So this is actually the profound reaction, or actually the fundamental reason why carboxylic acids are acidic, and how much this release of a proton, how much this release of proton is easy, or how easy the release of proton, or how difficult the release of proton is. That actually is the explanation or description of how acidic or how basic these carboxylic acids are. And this could be easily described using equation shown here, or using a formula shown here. It's called Ka, equilibrium constant. And for this reaction, so this is a general concept. You all know the equilibrium constant, how we define the equilibrium constant. Just for your, just to help you recall, if we have a reaction like this, then the equilibrium constant is what? The molar concentration of A and B over, molar concentration of C and D over molar concentration of A and D. This is D, A and B, right? Yeah, this is the definition of equilibrium constant for a given general reaction. And same is true for the release of proton reaction. And then eventually we have the equilibrium constant for this reaction like this. We exclude water, by the way. You also should know that water is not included in the equilibrium constant. And then what? We have Ka, the equilibrium constant for this reaction, and then we call this constant acid dissociation constant because it's for the dissociation reaction. The COO and the H plus, they are dissociated from COOH. And then eventually, if Ka is large, that means what? It's more acidic because more H plus is released, and therefore this number will increase, and therefore Ka will increase. However, if you compare Ka directly, it's kind of difficult. It's kind of difficult because sometimes because it has something like 4 point something times, let's say 4.7 or 7 times 10 to the negative 4, something like this. The numbers are long and can I say dirty? It's you don't want to handle like the something point something times 10 to the negative something. So simply you can take the negative log of Ka value, and then you can have what's a single digit maybe, or let's say 1.1 or 2.2 or something like that. We call it pKa. It's negative log. So if Ka increases, then pKa increases, then pKa decreases. So that's something that you need to know. So pH 1 and pH, let's say 13, pH 1 is more acidic than pH 13. So I am pretty sure you all know this, but as a reminder, I'm just giving you the brief review. And this has something to do with the formula, and therefore you will need to some math if necessary. So before we think about the detailed structures of carboxylic acids, maybe we need to consider why carboxylic acids are acidic. Meanwhile, alcohols having the same OH group, like the OH of carboxylic acid, is not practically not acidic. That's something that we need to consider. Let us think about the equilibrium equations for each material. In case of ROH, if it releases H+, then it should be RO- plus an oxonium ion. Meanwhile, in case of COOH, it releases H+, and then it becomes COO-. So if you compare both sides, maybe this is same. Okay, should I use the blue pen? It's the same. It's the same. And then we have a major difference with the product shown here, ROH and RCOOH. We need to compare these two species to understand why carboxylic acids are more acidic, much more acidic than alcohols. That is because of the stability of RCOOH. It's much more stable than RO-. And remember when we discussed the acidity of alcohols with different chain length, such as CH3OH and eventually CH2OH, let's say. So we had a series of alcohols, and then depending on the length of the alkyl chain, the acidity was different. And how did we explain that? Our explanation was that the remaining anion part, like CH3O-, and then here it's CCCCCO-. I omitted hydrogen. Which one is better solvated by the solvent molecules and therefore more stabilized. That determines how well these materials can release H plus. That's what we discussed before. And then as a result, methanol was determined to be the most acidic among the alcohols because it has a very short chain, alkyl chain CH3, and therefore the oxygen, the charged oxygen, can be easily stabilized by the water molecules solvation in case it's in water. And this kind of long chain cannot be easily solvated because it's hydrophobic, and therefore this anion is less stable than CH3O minus. This is much more stable. That was the logic. We can apply the same logic to these two species, RCOO and RO. But we are now at 2:45 now, 44. Yeah, it will be. Let's take a break for now, and then we will keep talking about the stability of RCOO minus and RO minus. Just tell you the conclusion first. RCOO minus is much more stable, and therefore it's better generated, and therefore it releases more H3 plus. I'm sorry, H3O plus or H plus. So stability of the product is important to explain the release of H plus. That's the same with the contents here and the contents here. Why COO minus is more stable? Then that's what we will discuss after the break. All right, so it's 2:45 now, and then we will come back at 2:50 after a 5-minute break. Right, see you soon. 네, 다시 어, 시작하도록 하겠습니다. Okay, we are back and then let us begin again. 그러면 끝날 시간을 생각하는 게 좋겠죠? 우리가 Yeah, we are going to be done at 4:05, right? Yeah, as we always have done so far. We're going to be over at 4:05 p.m. So, yeah, let's focus for about 1 hour more. 어, 어, 왜 안 좋아지지? 이거 안 좋아지? 어, I'm sorry, I cannot remove what I write right here. Then okay, it works now. All right, so remember the logic, the same logic should be applied to determine which species is more acidic when we compare alcohols and carboxylic acids. And the best way is to do the same thing as we did before with the series of alcohols. And as I told you, our course, I'm sorry, COO minus after the release of H plus is much more stable than RO minus. That is because of this issue, resonance stabilization, which will be discussed on the next slide. But this is the major issue to explain why RCOO minus is more stable than RO minus. This gives a significant change in terms of difference in terms of the pKa range. So, carboxylic acids are typically pH 5. Typically, it's like 4, 5, 6, or something like that. Meanwhile, in case of alcohols, pKa is approximately 16. So it's like as different as 10 to the 10th or 10 to the 10 to the 11th difference, like 10th order or 11th order difference between them. It's like huge difference. So this scheme explains why this is COOH, this is OH. If it's just O minus, then this is what it is supposed to be in terms of the energy level. But in case of COOH, when it becomes COO minus, there's additional stabilization. Even though they have the same negative charge, one single negative charge, there is an additional stabilization in for the carboxylic acid functional group. What is that? Yeah, it's based on the resonance. So think about the structure of COO minus. This is what we can imagine at the beginning. However, is it fair? Is it really fair that this oxygen carries only the negative? I'm sorry, only this oxygen carries a negative charge, and this oxygen feels free and comfortable? Not necessarily, because from the viewpoint of the carbon, when imagine you are the carbon atom, you have just a single you have one oxygen over there and oxygen over there. So they are all same oxygen atoms that are bonded to the carbon atom. So there's no reason for the carbon atom to discriminate the oxygen atoms. So if this is one possible structure, obviously carbon and oxygen bond and the electrons between them, they can easily be transferred to the other or another bonds. So here we have the two electrons right here that can be transferred to the bond, neighboring bond between the carbon and oxygen as well. And it is okay. Why? Because eventually there's no practically there's no difference between them. It's just the same electrons, but in a different CO bond. But still it's the same, actually, equivalent CO bond. So as a result, we have the same material, but now the negative charge is on the other oxygen atom, and they are equivalent, so there's an equilibrium between them. If you learned this concept in high school chemistry classes or even in middle school chemistry classes, probably some of you have heard that these two structures change very rapidly. So you expect something in the middle in terms of the structural properties. That's not true. It's not like rapidly changing between the two states, but actually there is one common intermediate state, stable intermediate state. It's not like the rapid changing between the two states. And this status actually is based on the structure like this. This carbon is here, and then oxygen is here, oxygen is here. There are, if we describe this structure first, there are two electrons in the p orbital of the oxygen, and then there's one electron pair for the sigma bond and another electron pair for the pi bond. So that's why we have double bond here, and then there's single bond here, and then negative charge right here. But as I told you, this could be easily changed, or let's say this structure could be also considered for these orbitals. So eventually, we have 1, 2, 3, 4 electrons. These are for the pi bond, right? And this is the unshared electron pair, lone pair. And then these are all mixed together. So eventually you have all overlapped p orbitals and so on. That's the final result, which is kind of described in this way. Actually, it's not half and half. It's all distributed evenly over the oxygen, carbon, and oxygen structure. It's evenly distributed. The negative charge is evenly distributed. All right, so it was a point charge before, like this or like that. And then after we consider the resonance, this is called resonance. Then now we have the result of the distributed charge. And as I have emphasized several times, if point charge is dispersed, then that is one way, a typical way to be stabilized. So that's what's happening right here. The p orbitals of carbon and oxygen, they share their electron cloud all together, and they share the electron cloud all together, and eventually the 4 electrons. It's also important. 4 electrons, 3. Here 4 electrons in the or across the 3 p orbitals are all delocalized. This is the important term. It's not just one point charge localized at a specific atom. It's not like that, but it's delocalized across the several orbitals, in this case 3 p orbitals. So negative charge is dispersed. That's the final conclusion that's the end of the explanation for the resonance of the COO minus anion. One more important part right here. What do we call it? COO minus. COO minus. We call it carboxylate. So it's carboxylate. A new term has shown up. So please be familiarized with the terms and concepts and detail the structures and then the delocalization of the electrons for additional stabilization and so on. Okay. So experimentally we have the examples of the formic acid and then formate, which is corresponding to carboxylate. So in case of the formic acid, there should be a difference in terms of the bond length. So C double bond O must be stronger because it's double bond, so it's shorter, 1.23 angstrom compared to 1.36 angstrom. It's very small scale, but still there is a difference between the two different types of CO-CO bonds. Meanwhile, in case of the carboxylate, the bond length between CO and CO, two oxygen bonds and one carbon atom, they are exactly the same. So this is experimental proof that the CO and CO bonds are equivalent, and therefore it's the that is the evidence for the possible resonance between the CO and 3p orbitals and 4 electrons. And I think that could be there could be other proof, other evidence for explaining the resonance behavior, but for now I think that's enough for us. So please understand what's going on with the COO minus or carboxylate anions in terms of the additional stabilization. We have a quick question from Kim Min-chan. Do we have to learn the nomenclature of carboxylic acid by heart? I think he's talking about this. Yeah, we have actually 3 new names. I'm pretty sure you already know acetic acid, what acetic acids are, so what acetic acid is. So it's already known. So new names are, well, formic acid, butyric acid, stearic acid, and succinic acid, and malonic acid. It's not 3. Oh, actually 4. 1, 2, 3, 4, 5, not 4. Yeah, you know what benzoic acid is. We already discussed that. So 5 new names, and also Greek letters for the indication of the carbon atoms. I think that's all you need to learn by heart. So for example, if something like this is given to you, not only the IUPAC nomenclature, but the conventional nomenclature name could be, well, could be asked in the exam. Possibly. Yeah, I'm not saying I'm going to ask, but possibly conventional names of some carboxylic acids could be the topics or the main issues of some questions in the final exam. But is it? Are there anything else? Yeah, I don't think so. Everything else is all known to you. The IP names are all known to you, and this is not nomenclature, so we don't need to consider as a nomenclature. It's just the properties. Yeah, so that's it. I believe this could be an answer to your question. All right, so it's time to think about the structure and property correlation. Structure property correlation is always an important issue with every material that we have discussed and that we will discuss in this course. And that actually is the main theme of material science and engineering: structure, property, correlation. You change the structure, you control structure to change the properties and control the properties of a given material. That is the basic theme, main theme of our subject. So please be familiarized with this concept if you haven't, as soon as possible. All right, so substituent effect. If you change something in the carboxylic acid structure or backbone, then the acidity could change. So from the backbone something structure, acidity change property. How? We will check it out. Tug of war. I just showed the scheme to explain what tug of war is in terms of concept. Yeah. Tug of war It's 줄다리기 in Korean. So that is a metaphor to describe that there could be two possible directions. If something withdraw, electron withdrawal, or something electron donating is bonded to the carboxylic acid functional group, like this or like that, then the acidity can change. For example, if this G is a kind of the symbol, is electron withdrawing group, then it pulls electrons density away from where? From the carboxylic acid functional group, or to be exact, carboxylate. After the release of H+, we are still talking about the stability of carboxylate, as we discussed with the acidity of carboxylate with alkoxide in the previous slide. So because the electron density is further dispersed because of the electron withdrawal of this G, and the anion will be more stabilized, and therefore this will strengthen the acid, which means it will become a stronger acid. Meanwhile, if there is an electron donating group that pushes the electron density will be pushed to the negatively charged carboxylate group, right? So electrons are pushed to this structure, and that means the charge becomes stronger instead of the dispersion. The point is becoming more and more point charge, or like more localized charge than before, which will destabilize the anion, and eventually that will weaken the acid, because the carboxylate is more unstable, no, less stable, let's say. It's less stable. That means it won't release H plus well, right? So it's like the tug of war, but well, it's kind of concept. So what is important is actually the explanations shown here and here. And it's about withdrawing the electron density, or withdrawing electrons or pushing electrons. We call things like that inductive effect, because um, electrons are pulled or pushed, and then that affects the final properties of the carboxylic acids, and that is why it's called inductive effect. And then that has something to do with the sigma bond, by the way. It's not about pi bond, it's sigma bond between G and C. It's a sigma bond. So there are some things that you need to clarify with yourself. And let's see how it works. Here we have an acidity spectrum. It's not a real spectrum. I mean, from the spectroscopy, it's more like there's something continuous from weak to strong. We have a representative acetic acid at the beginning. It's kind of weak acid in the series, in the spectrum. But if we have a chlorine atom bonded to this carbon, the carbon number 2, right? 1, 2. And 2 chlorine atoms and 3 chlorine atoms. What happens eventually? pKa decrease. It keeps decreasing, which means it becomes it becomes stronger and stronger acid. How does it happen? As we discussed in the previous slide, if there's an electronegative chlorine, then it withdraws, or let's say withdraw, or if we use a easier language, it pulls the electron from COO, potential COO minus, and therefore the charge is dispersed, and therefore it becomes more stabilized, and the more Cl we have, Cl atoms we have that in the carboxylic acid structure, the more electron density is pulled from COOH to the other side, and the more dispersed the electron density is, right? The more. Sounds good. All right, so that's the inductive effect based on the number of electron withdrawing group, electron withdrawing group in the structure of the carboxylic acid. There's one more variable that we need to consider, shown here, the distance. So in both cases now we have only one chlorine atom that is bonded to the carboxylic acid. However, in case of the left example, chlorine is kind of close to the carboxylic acid functional group. Actually, that's the closest possible position, right? However, the right example is here. This is carbon 1, 2, 3, 4. That's far away. So it's number 2 or number 4, right? The difference is number 2 and number 4. And look at the pH. If it's close to COOH, pK is quite low. Meanwhile, if Cl is far away from the COOH, then pK is only 4.5. Just practically the same as the carboxylic acid without Cl. Oh, they have different numbers, but without Cl, the pKa must be similar. Check out this pKa of butanoic acid without chlorine. This one. Yeah, pKa of this butanoic acid, and then 4-chlorobutanoic acid. I believe their pKa must be the same or very similar. Meanwhile, in case of 2-chlorobutanoic acid, has very low pKa. So it's very sensitive to the distance between the electron withdrawing group and the COOH. So number 1, inductive effective is additive. Why? Because the more chlorine atoms we have, the lower pKa is. So additive, more, then okay, it's increasing, or decreasing. But it drops up rapidly with distance. Just 2 carbon atom difference makes it nothing, but just pure, nothing different from the pure carboxylic acid. So 2 variables are important. Number of the electron withdrawing group and how strong the electron withdrawing group is, and also actually there are 3, right? 2 of them are shown here, and then one more thing. Can we compare this material with something like this, COOH and C and Br, right? Instead of chlorine, what about we have bromine that is bonded to the second carbon of acetic acid? Which one is supposed to be more acidic? Bromoacetic acid or chloroacetic acid? Yeah, based on what we have learned so far, bromine is more electronegative, and therefore it's more. This one is more acidic. Yeah, bromoacetic acid is more acidic than chloroacetic acid. Why? Because it has better power to withdraw electrons from COOH, and therefore more stabilized. All right, so again, let's summarize it again. Number 1, number of electron withdrawing groups, right? And number 2, how strong the electron withdrawing group is. Number 3, how far it is located from the COOH group. Yeah, those three variables are what you have to consider to determine or to compare the um, acidity of the carboxylic acid. Oh, it's shown here. Butyric acid of pKa is only 4.82, so slightly more acidic. But if you compare the acidity difference between this and this, it's almost negligible. It's acidic, definitely more acidic, but it's less effective. There's one more series to compare the acidity of now aromatic acids. Previously, it was aliphatic acids. Remember the terms aliphatic and aromatic? Aromatic is the compounds containing the benzene rings like this. Aliphatic is more like the linear structured. So use the terms to describe what you want to describe. In this case, it's about the aromatic acids and their relative acidity. Benzoic acid is the norm. That's the norm, the beginning point. If we have CH3, CH3, it's a little bit more complicated than what I'm going to tell you for now. But I think the best way is to understand it in a easier way, I think. So let's say it's not 100% true, but let's say CH3 is an alkyl group, so it pushes electrons. Pushes electrons. So what? There is COOH. Even though there's a benzene ring in the middle between the COOH and the alkyl group, still it works in a similar way. So if there's a COOH, then it's an electron donating group, and therefore it will destabilize COO minus, right? And therefore acidity will decrease from the regular benzoic acid, and therefore pKa increases, right, slightly. How about the nitrobenzoic acid? NO2 is nitro. How about that? It's electron withdrawing group, right? Because it's electronegative nitrogen, electronegative oxygen, and one more oxygen. So it's composed of electronegative species, and therefore NO2 is supposed to be electron withdrawing group, and therefore, again, even though there is the big benzene ring between NO2 and COOH, still it works in a similar way. It will decrease the electron density of what? COO minus, and therefore it will stabilize. It will stabilize the COO minus carboxylate, and therefore it will be more stable, and COO minus will be more stable, and therefore it's more acidic than the standard benzoic acid. One more thing, let's think about the distance. It's NO2 right here at the fourth position or para position, at the fourth carbon position. And then what about we have NO2 right here? It's closer, right? Closer than the number two position is closer than number four position. So it withdraws electrons better and more than the first position. So it's more acidic than the para nitrobenzoic acid. Although nitrobenzoic acid is more acidic than the para nitrobenzoic acid. So I think this explanation is quite similar to what I told you, but it's a little bit more, but that's too much complicated. So why don't you just think about just distance and electron withdrawal or electron donating effects, and I think that's enough. Instead of this ortho effect or fancy whatever, just think about electron donation or electron withdrawal, and also distance between them and things like that. There's a question from Kang Hyun Shi. Cl is more electronegative than Br, is it? Oh, right. I'm sorry. I made a mistake. Thanks so much for your clarification. Br is less electronegative because fluorine is the most electronegative element. And then I'm sorry, I'm confused. And then therefore fluorine is the most electronegative, and then chlorine is next, and bromine is next. So bromine is not more acidic, but it's less acidic. Thank you for your attention and clarification. All right, so yeah, therefore, bromine and iodine or fluorine, depending on which element you consider as a part of the carboxylic acid, you have to be able to consider their relative electron withdrawing or electron donating effects. So yeah, these things like CH3 or NO2, like this, these are called substituent because they are substituents for hydrogen, which originally was there. So electron donation, electron withdrawal, and proximity, how close they are located to COOH. That things, those kind of things dictate the acid strength, even in case of the aromatic acids. We have an example shown here. Wait. Yeah, we have an example of a list of a pKa depending on the structure of acids. On the top, this is the strongest acid, and on the bottom, this is the weakest acid in the list. Can we justify them? If I pick up any of them, and then can you justify that this is stronger than the other, and so on and so forth? Yes. For example, let's see number 1 and number 2. Yeah. It's difficult to call their names one by one, so let's number them and then let's use the numbers. Number 1 and number 2, which one is supposed to be stronger? Number 1. Why? Because just like we discussed before, fluorine is more electronegative than chlorine. The number of the electronegative atoms, the same, 3, right? And the distance from the carboxylic acid functional group, the same. So what else do we have to do? Yeah, the absolute strength, or I'm sorry, the absolute electronegative properties of F and Cl, and F is more electronegative, and therefore it will stabilize more the COO minus, and therefore it's more acidic. There should be then Br3, which is not shown in the list, but if there's something like Br3 3CCOOH, then this must be less acidic. Then Cl number 2. Yeah, this must be less acidic. Then Cl2. How about number 2 and number 3 and number 4 and number, there are more. Number 5. Number 5 is acetic acid, right? Let's say it's a standard. And then number 4, 1 chlorine. Number 3, 2 chlorine atoms. Number 2, 3 chlorine atoms. Therefore, number 5 is the least acidic, and number 2 is the most acidic. And this is also an example of the number of electron withdrawing group is important. And also, as we just discussed, 1 fluorine atom, it is number 5. 5 Br, iodine, 6, 7. If we compare 5, 6, and 7, then it's time to think about just what we discussed in the previous slide, or 2 slides ago, let's say. Iodine is the least electronegative, and fluorine is the most electronegative. Oh, here we have skipped one more thing. Here, number 4. 5, 4, 6, 7. Yeah, that's another series that we can compare based on the relative electronegativity of the electron withdrawing group. In this case, all halogen elements. And also here we have the example of chlorine here. This is number 8. And chlorine here. The same backbone structure, but the location of chlorine is different. There should be something else where chlorine is closer to carboxylic acid. Oh, right here. Number 8, 9, 10. Yeah. So if we compare number 10, number 8, number 9, then we can compare the relative acidity based on the location of chlorine, or let's say the distance between the chlorine and COOH. All right, so that's the full list of kind of familiar carboxylic acids with their relative comparison of pKa. I'm sorry, yeah, comparison of the acidity with the exact numbers of Ka and pKa. So be familiarized with this table and then try to understand when you pick up some of them. Try to understand their relative acidity based on their structures. Okay, so this has been the long session for the properties of carboxylic acids, the acidity, boiling points like physical properties and things like that. Now let's move on to the reactions now. So it has C double bond O, so this we know that this carbon is partially positively charged. However, if this is the case, then we may expect the same reactions with the carbonic compounds, right? The nucleophilic addition and things like that. However, in this case, it's not that easy because this nucleophile may attack this carbon atom of the carboxylic acid, which means the OH must leave, which is not easy. Why? Because this OH or hydroxy group is very poor leaving group. We discussed this before when we were at the our core functional group, and I think this is one of the midterm exams, right? Why OH cannot leave easily and why protonated OH or OH2 plus can leave easily. What makes the fundamental difference between them? That was the question, right? I'm still preparing the Jae-Seung material, so I'm sorry for the delay, but we will discuss this there again. But think about that. OH minus cannot leave easily. So that means this carboxylic acid is not that much reactive. And also think about the oxidation reactions. Remember, primary alcohol is oxidized to aldehyde. Aldehyde is oxidized to carboxylic acid. And carboxylic acid is the dead end. There's no more product after the oxidation of carboxylic acid, right? So again, from there are so many clues telling us that carboxylic acid is not that reactive. From theory, from the structure, and also from the observation. So how can we, this is the goal, how can we make carboxylic acid reactive? How can we do that? We have to transform the acid into other functional derivatives to make them reactive. Derivatives, remember this term? Yeah. The best way probably to understand derivative is family. Yeah, functional families. Something similar but slightly different. Then to do so, we must take a strategic chemical detour. You know what detour is? This is going straight, and then this is this is detour. What is detour in Korean? 돌아가세요? 저쪽으로 돌아가세요 하는 그런 표지가 maybe detour, I think. I don't know what exact word could be used for detour. Anyway, that's the meaning of detour. So we cannot directly use carboxylic acid for their direct reactions. So we need to convert it to something else and then react the converted function or derivative for the reaction. That's the meaning of detour. 우회. Thank you. 김민철 씨, thank you. Thank you. Thank you. 네, 우회. I'm sorry. This is the problem of being old. Yeah, if we become old, then things does not come up from your mind. So sad. Anyway, yeah, 우회하다, detour. It's good to know. 속이 시원한데요. 계속 뭐지 하고 있었는데 detour, 우회하다. Anyway, let's move on to the reactions of carboxylic acid. And before that, we have to think about the nucleophilic acid substitution. Why all of a sudden we have something like this? Where's carboxylic acid? Yeah, it will show up later. But let us think about the reaction of RCOCl. Yeah, it looks similar to carbonic compound, right? Yeah, maybe it will react in the same or similar way. But let's see. Let's say we have this compound at the beginning, and then it reacts with nucleophile because this carbonic carbon is partially positively charged. By the way, this kind of material, RCOCl, it's called acid chloride. It's acid chloride. So the name tells us that it comes from it came from acid, carboxylic acid. So we'll see why or how. But anyway, it's called acid chloride. Chlorine is here, so it's chloride, and it was originally carboxylic acid, so why it's called acid. All right, so nucleophile attacks the carbon right here, and then the same intermediate structure is formed. We should be familiar with this intermediate structure now, right? Because we have seen things like this before many times. And what happens here? Yeah, I told you, oxygen is not happy because it's all of a sudden carries a negative charge because of this new bonding formation between the nucleophile and the carbon right here. So what does it do? Oxygen, I don't want to carry this charge. I'm going to give it back to you, carbon. So it gives the electrons back to the carbon and then forms a double bond again. Now what? Carbon has to take care of this problem of 5 bond formation, right? So it should give up one more. I'm sorry, not one more, just one covalent bond. So the best living group here is Cl, because Cl minus can live like this and stay there stably. So this bond is broken, and then Cl minus is released, the chloride ion is released, and eventually it has RCO and nucleophile. So addition and elimination takes place sequentially. And this is called acid derivative. Acid chloride, acid derivative, they commonly have C double bond O structure, and then instead of OH, it has either Cl or nucleophile. Depending on what nucleophile you use, the name could be different. So in case of aldehydes and ketones, they undergo simple addition, right? But in case of, and then eventually it becomes OH, remember, right? However, acid compounds like these are called acid compounds or acid chloride, acid compounds. They are all the same. And here, that's why we say acid substitution. It undergoes the 2-step, dance. So addition first, and then elimination. So there's a double bond formation again between carbon and oxygen. Again, why do we all of a sudden, why do we have to learn this? We were talking about carboxylic acid, and then why the nucleophilic acid substitution? Because we need to do this to use carboxylic acid. All right, so this is carboxylic acid. Energetically, it's very stable, right? So it's on the bottom. It does not react well. So people made a way to make carboxylic acid react by converting it into something else. That is RCO. So instead of OH, now it has Cl, which is acid chloride. And then once it becomes an acid chloride, it can readily react with other materials, which we'll see later. So how can we convert the stable carboxylic acid to acid chloride? How can we convert it? There's a magic compound, magic reagent, SOCl2, which looks like this. SOCl2, you can add SOCl2 to carboxylic acid to convert it into RCOCl, which could be, if we write the full equation, this could be the equation that we need to write. There are side products, but you don't need to know them. What is important is that RCOOH becomes RCOCl. We are going to skip the details about how we can convert, or how SOCl2 converts the carboxylic acids into acid chloride. We'll skip it because it's too much complicated. It's out of our scope. But what is important is that SOCl2 is used to convert carboxylic acid into acid chloride, and once acid chloride is formed, then following this addition and elimination or nucleophilic acid substitution, you can synthesize any material that you want using the appropriate nucleophile. So that's it. Once you reach the summit, well, that's the acid chloride, then rest of that is very easy because you only need to go down. Just like climbing a mountain, right? Yeah. Do you like it? I don't. Anyway, but it's similar and in terms of the energy. So both carbon, oxygen, and chlorine are electron withdrawing and thus make the carbonic carbon very electrophile right here. This carbon, this carbon is very it's very electrophile, right? It reacts with the nucleophiles very well, right? Therefore, or partially positively charged, and therefore, acid chlorides are very reactive with nucleophiles, as we have seen just before in the previous slide. So, converting the stable acid, carboxylic acid, into highly reactive acid chloride, by doing that, we unlock the ability to cascade down into any other functional derivative. It's necessary. You will see what kind of materials can be synthesized using acid chloride from here. The first example shown is the case of anhydride and esters. Both might be unfamiliar to you, although I told you you need to know what esters are before, and you should know, right? Our esters are like, where is it? It's R C O O R. This is the typical example of the structure of an ester. And then a little bit specific case, a little bit special case of ester formation is shown here using the concept of anhydride. What's the meaning of anhydride? AN means opposite. opposite, or no, which means it means negative. It means something negative. Hydrides. It has something to do with water. So there's no water. Water has been removed, or there, in other way, there's no water for now, but water can be added, or something like that. So um, it's similar to anhydrous, the adjective form, but let's say for now it means something like this. It's originally something like ROO, uh, 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 two carboxylic acid, let's say two carboxylic acid, and then R plus R CO, I'm sorry, OH and R COOH. When they're combined together, one water can be removed, OH, and H could be removed. And then the remaining parts could be um, combined together to form an anhydride. It's not made in that way. It's not made in that way, but um, directly. But if you consider only the results, then probably this is one way to understand it in an easier way, and that's why we call it anhydride. Water molecule has been removed. Okay, then anyway, that's for your understanding, and then let's move on to what is shown here. That's more important. All right, so you can synthesize anhydride using carboxylic acid. Yeah, we need to, first of all, this is the goal. You need to synthesize anhydride. That's the goal. Then how can we do that using carboxylic acid? That is the that is the thing that we need to consider. And then let us begin with acyl chloride. Yeah, we did that. How? Using SOCl2, right? So there was an RCOOH before, and then we used SOCl2 to synthesize acyl chloride, and then prepare carboxylate salt. How? You can neutralize the carboxylic acid using bases, right? Just add NaOH, then it will result in Na or RCOONA, right? Then what? Now you have an anion right here, RCOO minus, and then also acidic chloride, which is prepared previously. Combine them together, and as we have discussed, this carbonic carbon is extremely reactive because it's um, bonded with electronegative oxygen, electronegative chlorine at the same time. So this anion, the negative charge, attacks the carbonic carbon because it's a good nucleophile. This is N. Sorry. This is NUC. Yeah, nucleophile. So this is the intermediate structure, obviously, and then oxygen again. I don't like to have carry the negative charge, so it's yours carbon. So send them back to carbon, so that there's a double bond formation again, and then chlorine leaves. It's a good leaving group. So finally, we have a structure like this plus NaCl. Na was here, right? So chlorine, Na plus, they are combined together to form a salt like this. That is anhydride. And this anhydride, think about the reactivity of anhydride, right? This is carbon, this is carbon. These carbons are very, well, electrophile. It's partially positively charged, and they are ready to react with other nucleophiles. Why? Because they are bonded again with oxygen and oxygen. So obviously, one good example of using the anhydride is to synthesize this material. So it's called salicylic acid. It's a carboxylic acid, and it's excuse me, it's salicylic acid, and it's a conventional name. Salicylic acid is a conventional name. It's kind of maybe 2-hydroxybenzoic acid, I think. Yeah. Anyway, this salicylic acid comes from nature, from some plants, and then once you synthesize this acetic anhydride, the detailed name is acetic anhydride, where this R is methyl and this R prime is methyl, right? So this acetic anhydride reacts with the salicylic acid, then this oxygen, um, where is it? Yeah, this oxygen can attack the carbonic carbon of this red part of the anhydride, and then it will have some sort of this kind of intermediate structures, and eventually this part will leave. So there's a new bond formation between this oxygen and this carbon like this, and then we have acetic acid as a side product. So why do we have to synthesize things like this? What is there anything special with this? Yeah, there's something special with this. Its another name is aspirin. Yeah, so this is how we synthesize aspirin, which is important medicine for people. Some people need painkillers, right? So yeah, this is how we synthesize aspirin. And then to synthesize this, we obtain salicylic acid from, well, previously it was from nature, but I think there should be other methods to synthesize salicylic acid easily. And once you obtain salicylic acid, prepare acetic anhydride to synthesize salicylic. I'm sorry. To synthesize aspirin in following this reaction. So this could be one way to emphasize why anhydride is important. Another example shown here is the synthesis of amides and lactones, again using carboxylic acid, but not directly, but using acetic chloride. So you see all the examples are beginning with acetic chloride because we assume that carboxylic acids are already converted into acetic chlorides using SOCl2, right? That's the first reaction, which is hidden for now. And then later, the acetic chloride reacts with, first of all, ammonia or amines, primary amines, I think. Then this will become something like this because there are electron pairs that can attack the carbonic carbon. Remember the nucleophiles, strong nucleophiles and then weak nucleophiles. Ammonia was in the column of weak nucleophile. It was one of them. So it's weak, but still it is nucleophile. So it attacks the partially positively charged carbon of the carbonyl structure to have something like this. How does it work? So there are so many mechanisms, but if you take a look at them carefully, you know that they're all the same. So don't be confused, don't be scared, and then just try to understand the common features between or among the mechanisms. It's the same right here. We have, in this case, a primary amine as an example of the nucleophile, and as always, it attacks the partially positively charged carbonic carbon, and then oxygen always takes the burden to carry the electrons from the carbonic carbon, and what? It doesn't want to have it. It doesn't want to have it. Oxygen doesn't want to carry the charge. Doesn't want to carry the negative charge, so it goes back again, and then, as always, chlorine leaves. What is a little bit special or a little bit unique with this amide formation is that what happens with this amine, primary amine. So there are so many amine molecules in this reaction system, and then amines are bases, so they can take H plus. Why do we need that? Because this nitrogen, which was okay before, is now carrying one positive charge. It doesn't want to, but it has to, right? For now, because of the one more bond formation between the nitrogen and carbon right here. So it's kind of ammonium, right? And it doesn't want to carry the positive charge. So therefore, therefore, the it it releases the nitrogen releases one hydrogen, and then this hydrogen is taken by the other waiting primary amines, so they become ammonium or whatever, and then now nitrogen is happy because it has now three bonds, one H, one R, and then the bond with the carbon atom, and then as always, chlorine leaves. And finally, we have RCO and HR, and this is the side product. This ammonium comes here with chloride anion to balance the charge. This structure is called amide. It's unique right here. C, the bond O, and N. This is called amide. So make sure you understand the structure. You understand the structure. You can identify the structure, and then you know what name is, what kind of class this material belongs to. Like the ester, we skipped all the nomenclature for esters. Same is true with amide. Maybe you don't need to know the detailed IUPAC nomenclature for amides, but you should be able to identify that this type of structure is called amide. This amide is unique because it has the capability to form hydrogen bonding each other like this. So the boiling point of amide is relatively high compared to other materials having similar molecular weights because of this hydrogen bonding issue. What about lactones? Lactones. It's a cyclic ether. So it's interesting. It's interesting. Let's see. You have carboxylic acid, or actually the anionic form of carboxylic acid. So here we have COOH previously, and now it's COO minus, and then C, and OH. If this R is H, then it's similar to. It's not similar. It is GBH. What we discussed before, right? I'm not pleasant with the name GBH or the material itself, but well, from the scientific viewpoint, we have to deal with that. Anyway, it's a COO minus and OH. So anyway, we have COOH in an anionic form, and then OH. So these could be combined together to become COO RR plus H2O, right? One water molecule can be removed from here. And that's what happened. This OH reacts with COO minus to become this cyclic compound. So intramolecular reaction takes place. In the same molecule, the part of the molecule and the part of the molecule react together. That is the meaning of intramolecular reaction. And what kind of reaction? Cyclization, because it becomes a cyclic material. So hydroxy group and the carboxyl group, they react together, and one water molecule is generated as a side product. Again, we are not going to go into details of the lactone formation because the mechanism is quite complicated. So I just want to let you know that it's possible to react OH and then COOH together to have COO. Yeah, that's all I want. Like this. That's what I want to let you know. And then that reaction is more discussed right here. We just discussed that alcohols like OH and then carboxylic acid COOH can react together to become RCO. I'm sorry, COO and then R and R. This COO is called ester, as we all know. And then I told you water is generated in case of lactone synthesis as a side product. How does it happen? How is it possible? If there's, we know that the ester can be ideally synthesized if we only consider the molecular formula. Like there's an OH, there's a COOH, so they can be COO, I'm saying RCOO, and then water molecule is generated. One water is eliminated, for example. This is, if we only consider formula, then we can easily understand that this could be possible. But in terms of chemical reaction, is this really possible? If there's a OH, if there's a COH, then is this really possible that this reaction goes by itself without any heating or any kind of yeah, I mean without any catalyst or without any using acidic chloride? Don't we need to do this? We just discussed that carboxylic acids are unreactive or very less reactive. So how is it possible that carboxylic acid actually can react with alcohols if carboxylic acid is not that reactive and should be converted into C acidic chloride? How is it possible? Yeah, that could be the appropriate question at this point. So the answer is yeah, it is not impossible. It is not impossible that the carboxylic acid reacts with something else. Yeah, that's the point. So it's not a favorable reaction. It does not go very well with a high yield. It's kind of okay reaction, but it is not impossible to run this reaction. That is probably what we that's probably the appropriate understanding for this reaction. So let's take a look. So acid, yeah, as itself reacts with alcohols to become ester and water, following the mechanism shown here. Okay, so now let us begin with carboxylic acid. It's weird, right? So far we have been thinking about just acid chloride like this, right? But now it's carboxylic acid. So let us begin the real carboxylic acid reaction. Okay, so under acidic conditions, the carbonyl oxygen is protonated first, right? And then once it's protonated, we discussed this in case of the carbonyl compound. If carbonyl oxygen is protonated, then this carbon has a little bit more partial positive charge and better to be attacked by nucleophiles. Remember that? There's the kind of resonance structure, so it has more partial positive charge and things like that. So our course, and more specifically the oxygen with the lone pairs, unshared electron pairs of the alcohol can attack this carbonyl carbon. So this is the intermediate structure. Now the red part is the alcohol, and the black and the blue part is the carboxylic acid. Because of the transfer of the electrons to the oxygen side, now it has become a single bond, right, between the oxygen and carbonyl carbon, and the positive charge of the oxygen has been eliminated because of the transfer of the electrons. So this part, everyone is happy, right? This part, everyone is happy. How about the alcohol? Okay, so alcohol was okay by itself, but after the attack, now there is the electron donation to form a bond between the oxygen and the carbonyl carbon, right? So oxygen donated 2 electrons to form the bond, covalent bond with the carbon atom. Therefore, covalent bond must be the electrons there, because covalent bond must have 2 electrons per bond, and those 2 electrons must be donated from each atoms. But in this case, oxygen atom donated 2 electrons by itself. So that means after the formation, bond formation, oxygen is positively charged because it practically lost 1 electron to be shared with the carbon atom. So not happy. Again, oxygen is not happy because of the positive charge. So what? The best way to eliminate the positive charge is to release something positively charged, the leaving group that is positively charged. And that category tells us something like H plus, right? Good leaving group that is positively charged. Typically, that's a proton. So proton is released, and then this bond is cleaved, and then these electrons are used to form to neutralize the positive charge of the oxygen. So eventually, this is the kind of stable intermediate, but it's not done yet. So after several more steps, so these are step 1, this is step 1, step 2, this is step 3, there are 3 more steps up to step 6. I do not want you to go all through the 6 steps for this reaction. So let's say this is as far as we understand. And then what happens by somehow by some reactions, this H and this OH are removed. And then there's the double bond formation again. So eventually we have an ester like this. So we need acid conditions, right? For the protonation of the carbonyl oxygen, or carboxylase oxygen of C double bond O. So it's an acid catalyzed equilibrium reaction, and we learned only half of the reaction because of the scope issue of our subject. It's called Fischer esterification. This guy developed this reaction, and then it does not require much energy or much reagents, just acidic conditions. That's all it wants. Its yield is not that good. But still, it goes in this way. Esters are used for scent, perfumes. So if you fermentate wines, for example, for a long time, or alcoholic beverages for a long time, then this kind of esterification takes place automatically by nature, by itself. And then that's why after certain fermentation or certain period of storage, the alcohols like wines or whiskeys, they have some flavor, unique flavor. That's because of the formation of this kind of ester materials under acidic conditions. And we call it Fischer esterification and then esterification. And then that means acid and alcohols can react together without any further assistance of acid chloride. Acid chloride is right here. And then that can explain why lactones can be formed easily, because it's basically the combination of OH and COOH. Just one simple particular stuff or thing is that it happens in an intramolecular reaction way. All right, so we have the table showing different functional derivatives. Acid chloride, this is important because we have to convert carboxylic acid into acid chloride to let the reaction go. And anhydride, or COOH, COOCO, yes, it's just a reactive, and then it could be synthesized using acid chloride. Oh, by the way, acid chloride is synthesized using SOCr2, and once it's synthesized, it can be used for the synthesis of anhydride for the synthesis of esters and for the synthesis of amide. So remember, acid chloride is important. Chloride is important for the synthesis of other functional derivatives from the carboxylic acid. But acid chloride is synthesized using SOCl2. Other side products are synthesized in this way, and reactivity, it's very reactive, and then it's less reactive, more, let's say, unreactive. Boiling point, it's kind of okay, medium, low, but amide has very high boiling points because of the hydrogen bonding formation. And then they have different leaving groups, so please try to understand the types of leaving groups depending on the functional derivatives during their synthesis or using their for their synthesis. And then, do we have more? Oh, remain 2 more pages. Okay, we can take care of them later, but we are almost there, right? Oh, we have a question from Kim In-cheon. Lactone, oh, it's not lactone, lactones. But anyway, lactones, it's a COO minus, but it's a C. Did I say COOH? What is the difference between them? Oh, so it begins with COOH minus, but look at this. Yeah, we have to add H plus so that it becomes COOH eventually. How about that? Yeah. So this is just typical reagent that people use to synthesize lactones. It begins with a salt form, and then they add acid to convert it to COOH. Right. So it's a good point, right? So you may use just the form like RCH, CH2, CH2, COOH. Either this or CO minus is okay. Yeah, you can use both forms. But what is important is anyway, you have to use the acidic conditions by adding acid. Just like the Fischer esterification, you have to add acid to run the reaction. All right, so a little bit we are over time, but I think that's it, right? we 4시 5분에 끝내는 거 맞죠? 네. So okay, so we are done for today, and then thank you so much for your participation. It's we have 35 people, and then I believe others will watch this video later. All right, so thank you so much for your attention and attendance, and then enjoy your weekend, and then we'll see on Tuesday, next Tuesday. Thank you. See you later.